Good morning. Today we will discuss a topic in computational fluid dynamics. The topic name is classification of partial differential equations. Myself, I am P. Venkata Mahesh, Assistant Professor in Mechanical Engineering Department, Institute of Aeronautical Engineering. Now, why we have to see the classification of partial differential equations? Okay, that is one question. And what are the partial differential equations? What are called as partial differential equations, that we will see. Now, in an equation, if all the derivatives, the partial derivatives of the dependent variables are there, all the terms, see here, there are many equations. In this, these are the dependent variables, u, v, u, all the u is the dependent variables. Now, these are the partial differentiation of u with t. Okay, this is partial differentiation of u with x, and this is also partial differentiation of u with t. So, if the equation contains this kind of partial differential terms, then the equation is called the partial differential equation. Okay. So, there are two types of variables. One is dependent variables and the other one is independent variables. So, here the time x, y, z, the space coordinates and time coordinates, they are independent variables, and the velocity, pressure, density, all those things come under the dependent variables. So, equation may contain one or more dependent variables, and it may even contain one or more independent variables. So, as you can see here, there are many, here two independent variables are there, one dependent variable is there, and here two independent variables and one dependent variable, here also two dependent variables and one independent variable, and in these two equations also the same case. So, there can be more than one dependent variable and there can be more than one independent variable in the partial differential equations. Now, there is a term called the order of the partial differential equation. So, what is this order of the partial differential equation? So, here in this equation, if you see, the highest derivative is second order. So, this equation is called second order partial differential equation. So, in any equation, we have to identify what is the highest derivative term, and that gives the order of the partial differential equation. Then, there are two things called linear partial differential equations and non-linear partial differential equations. Okay, if all the partial derivatives are of order of 1, okay, degree, the degree of the partial differential terms in the partial differential equation is 1. 1 degree means the power. See here power is 2. So, the degree is 2. And here in all the other partial differential terms here, the degree is 1. So, if the partial differential equation is containing the partial differential terms, all of them as 1 degree at most, then such a equation is called linear partial differential equation. If the degree of any one term is more than 1, then it is called a non-linear partial differential equations. So, these are the few things about partial differential equations. Now, is there any other classification? There is a subset of, the quasi-linear partial differential equation is there. This is you cannot say that all linear partial differentiations are quasi-linear partial differentiation. Okay, your quasi-linear partial differential equation. Okay, so, and linear partial differential equation. So, requirement of quasi-linear partial differential equation is the highest order should have only 1 degree. Okay, so here it is a second order and the degree is 1, and here also the second order, the degree is 1. If the remaining partial differential terms are having the degree more than 1, it doesn't matter. For linear quasi-linear partial differential equations, the condition is that the highest derivative must be linear. Okay, the highest derivative must be linear, and the remaining terms it can be non-linear. So all the linear partial differential equations can be classified as quasi-linear partial differential equations, because in both the case the highest derivative is the linear term, and in linear partial differential equation all the terms are linear. So if I take any linear partial differential equation, you can say it is a quasi-linear partial differential equation. But the otherwise, the contrary of this statement is not correct. All the quasi-linear partial differential equations cannot be called as linear partial differential equations, because the linear partial differential equations, all the terms must be linear. But in quasi-linear partial differential equations, only the highest order must be linear. Okay, so that is the difference between quasi-linear partial differential equations and linear partial differential equations. Coming to the governing equations that we have derived till now, we have derived for inviscid flows and viscous flows. Now in inviscid flows, the highest order is 1. Okay, in inviscid flow the highest order is 1, and they are always linear terms. And in viscous flows the highest derivative order is second order, and here also they are linear in nature. So these governing equations for CFD, they are the quasi-linear type of equations. So the the highest order is 1 in case of viscous flow, and the highest order is in the 2 in case of the highest order in case of inviscid flow is 1, and the highest order in case of viscous flow is 2. In either case, the highest order is a linear term, or the degree is 1. So it can be called as a quasi-linear partial differential equation. So the remaining terms can be having anything, but the highest order is linear. That's why they are called quasi-linear partial differential equations. Now here we have to classify the quasi-linear partial differential equations. Why we have to classify the quasi-linear partial differential equations? The classification here we are doing based on the mathematical behavior. Okay. Now if I find the solution of a partial differential equation, then the solution must follow according to the mathematical behavior of the equation. So before finding the solution, what I should do, I should understand the quasi-linear equation or the governing equation that I am having, whether it is a elliptic equation or parabolic equation or hyperbolic equation, based on the mathematical behavior. So that is what we are going to see in this class. Now here we have taken two equations. These are the two equations that we have taken, and these two equations they are linear. Okay, so they can be called as a quasi-linear as well. Okay, and we have taken a point P here. Okay, we are considering one point P, and this point P is in a two-dimensional space, in xy space. Okay, this is y direction and this is x direction. We are taking a point P in an xy plane. Okay, now u and v, in this equation you can see u and v and x and y. So what are these u and v and x and y? The u and v are the dependent variables, and x and y are the independent variables. Now the u and v are the continuous functions of x and y. So that is what we have taken. So u and v are dependent variables. They are the continuous functions of x and y, and they represent the continuous velocity field. Okay, they represent a continuous velocity field in the entire xy space that we are considering. So what we are taking, we have taken a xy space, and in that xy space we have considered a point P, and the xy space we have two dependent variables called u and v, which are continuous functions of x and y. And the remaining terms a1, a2, b1, b2, c1, c2, d1, d2 are and f1, f2 are functions of, okay, they are functions of x, y, u and v. They can be functions of x, y, u and v. Okay, all these coefficients are the functions of x, y, u and v. So that is, these are the characteristics of this equation. Okay, now any point in xy space has unique value of u and unique value of v. So as you all know, in xy space, if I take, I have, say suppose this point xi, this point I have taken. Here I will have x1, y1, say suppose. And if I take a point in the, at this particular place, then it is x2, y2. Okay. Now these x1, y1 values are unique to that particular point. Similarly, the values of u and v are also unique for that particular point. That is what the next consideration that we are taking. And then the derivatives of u and v, okay, not only that u and v, the derivatives of u and v are also finite values at that given point. So what are the derivatives of u and v? It is dou u by dou x, dou u by dou y, dou v by dou x and dou v by dou y. So all these derivatives of u and v, they are finite values at that particular point. So any point I can take in the space, what I am considering is that particular point is having unique values of x and y. Similarly, it will also have unique values of u and v, and it will also have a finite values of the derivatives of u and v. So these are the few considerations I am taking for this space and these equations. Now let us consider this point P. Okay, this point P is in the xy plane. Now let us imagine the lines through the point along which the derivatives of u and v are indeterminate and continuous and called characteristics lines. So we will come back to this characteristic lines in few slides. We will come back to this. First, what we are doing, after considering the two equations, we are considering that u and v are continuous functions of x and y. Now, when u and v are continuous functions of x and y, the total derivative of du can be expressed like this, and the total derivative of v can be expressed like this. So, what is this? The u is function of x and y. So, what I am doing is, I am partially differentiating with respect to x and partially differentiating with respect to y, and I am multiplying with dx and dy. So, this is the total derivative of u in space xy, and this is the total derivative of v in space xy. So we have four equations, two equations in the form of the quasi-linear equations that we have taken, and two equations in the form of the derivatives. So these are the four set of equations. Now what we are doing, these four set of equations can be represented in the form of a matrix, and the matrix is like this. So here the coefficients 1, 2, 3, 4, 5, 6, 7, 8, and here we have dx, dy, dx, dy. All these are this is the coefficient matrix. Okay, this is the coefficient matrix, and dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y. So this matrix is the variable matrix, and this is the constant matrix. And the constants we have here f1, f2, du, dv. These are the, this is one, and here this is one column vector, and this is another column vector, and this is a matrix 4 by 4 matrix. So what we have done is, we have considered two quasi-linear partial differential equations in terms of u, v, x, y, and we have taken the concept of total derivative, and we got two more equations du and dy, and using these four equations we have formed the matrix. Okay, we have expressed all these 4 equations in the form of a matrix. Now I can find out the values of dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y using the Cramer's rule. What is this Cramer's rule? The Cramer's rule says that, say if I want to find out the value of dou u by dou x, what I have to do? The first column I have to replace with this column vector. The first column I have to replace with the column vector and find the determinant of this and divide it by the determinant of this coefficient matrix. So if I do like that, I will get the value of dou u by dou x. Similarly, I can find the value of dou u by dou y. How to do that? If I replace the second column if I replace with this column vector, and numerator numerator will be this and denominator will be as it is. Like that, I can find out the values of dou u by dou x, dou u by dou y, dou v by dou x, and dou v by dou y. These values I can find out using this Cramer's rule. Now I am imagining a curve AB. Okay, this AB curve is there, and I am imagining a curve passing through AB, through this point P, and it is represented by the A and B. Okay, I am imagining a curve AB passing through point P. Now along this curve, if P moves an infinitely small distance, okay, along this curve, the P is moving a infinitely small distance up to point 2. So point P is there, it is on the curve AB, and along the curve, the point is moving to a distance of ds, which is infinitely small, and it is reaching a point 2. Now what is the distance between point 2 and P? It is a ds, as the distance moved by the point is ds. Now the x component, here it is x2, y2, and here it is xp, yp. So these are the coordinates of these 2 points. Now what is the distance in x directions? The distance moved in x direction and the distance moved in y direction, that I have to calculate. So the distance moved in x direction is equal to the difference between the x coordinates. So that is x2 minus xp. The distance moved in the y direction is the difference between the y coordinates, and that is equal to y2 minus yp. Now as we have already assumed that the velocities are unique at the given points. So if I consider velocities now, the velocities are up and vp at this particular point, and here it is u2, v2. So because that is our initial assumption, that the velocities at a given point, at each point, are unique values. Okay, so now what is the change in velocity in x component? Okay, change in velocity of x component is difference between the x component velocities. Similarly, what is the change in y component of velocity is the difference between the y components of the velocities at 2 points. So you can find out what is dx, you can find out what is dy, you can find out what is du, and you can find out what is dv. Now if I substitute these dx, dy, du, dv values in this equation, I can find out what is the value of dou u by dou x at this particular point P. Okay. Now to what extent I am getting? What is the limiting condition for this? So the limiting condition is that this delta ds is tending to 0, infinitely small. Okay, the ds is tending to 0 means the dx and the dy are also tending to 0. Okay, so the value of dou u by dou x that we are getting is the limiting value of dx and dy tending to 0. Okay. So what we are getting from this equation is a limiting value of dou u by dou x tending to delta dx, where dx and dy are tending to 0. Since we have moved a distance of infinitely small, that means that the ds is tending to 0. Now let us consider another curve. The curve is, let's say, suppose CD is the curve. And if I do the same thing, whatever I have done for the movement of the point P along the curve AB, if I do the same iterations and find the values of dx, dy, du, dv, what I will get? I will get another value of dou u by dou x. Okay, I will get another value of dou u by dou x for the limiting case of dx tends to 0 and dy tends to 0. What we can observe is the values of dx, dy, du, dv, they are different. Okay, but the value of dou u by dou x will be same. Okay, the values of the dx, dy, du, dv, they are different, but the dou u by dou x is same, because the dou u by dou x we are speaking is of the point P. Okay, the dou u by dou x is related to P and the point is fixed irrespective of the direction of the curve that we are passing. And we are doing, we are going to an infinitely small distance. So infinitely small distance, it doesn't matter whether we are taking the curve AB or curve CD, but we will get the same value of dou u by dou x for the limiting case of dx tends to 0 and dy tends to 0. So this is about this Cramer's rule. By using the Cramer's rule, we have found out what is the value of dou u by dou x. Similarly, I can find out the values of dou u by dou y, dou v by dou x and dou v by dou y. So here the direction is only arbitrarily we have taken. So it doesn't matter in which direction we are going, we will get all the same values when dx tends to 0. Now there will be a curve called EF. Okay, there will be a curve called EF, and that curve is called the characteristic line. Now when we say this, it is a characteristic line when the dou u by dou x is equal to 0. Okay, when this is 0, when this value is when dou u by dou x is indeterminate. When dou u by dou x is indeterminate, then the curve along which we are passing is called the characteristic curve. Now for this dou u by dou x to be indeterminate or the curve to be characteristic curve, what is the condition? The denominator must be equal to 0. The denominator the determinant of a must be equal to 0. Okay. Now in such case, what happens is the value is not possible to calculate. Okay, the value is indeterminate. We will not be able to calculate, or it is not possible to calculate. So if such characteristic curve exists, okay, this is an imaginary curve. If such characteristic curve exists, what is it meaning? The denominator is equal to 0. So now we are building on that point called the characteristic curve. So we are imagining a characteristic curve and we are saying that the denominator, the determinant of a is equal to 0. Okay. Now this is what we are saying, the determinant is equal to 0. Now at what point the determinant will be equal to 0, that we have to find out. So what I have to do, I have to expand this determinant. If I expand this determinant, I will get an equation in terms of, now the derivatives of u and v are indeterminate if this equal to 0. This is what my statement is. Now the characteristic lines are independent of whether we are solving for this. You are solving dou u by dou x or dou v by dou u by dou y or dou v by dou x or dou v by dou y. Whichever value may be calculating, the denominator is not changing. The denominator is always determinant of a. This is the a, and the determinant of a is equal to 0. That is what is the characteristic line. Now what I have to do, I have to find out the slope. Okay, I have to find out the slope of this equation. How to find out? I want to find dx by dy or dy by dx. This value I have to find out. So how to find out this value? By expanding this determinant. So if I expand the determinant, what I will get? I will get this equation. Okay. So what I have to do? I have to multiply with this, with determinant of this small matrix, plus I have to multiply this with determinant of these 6 elements, and I have to multiply this with determinant of these 6 elements. If I simplify that, what I will get? I will get this as the expansion of this determinant. Now if I divide these equations with respect to dx square, what I will get? I will get this equation. Now this is a equation and this is the slope. Okay, this is the slope which we are looking for. The dy by dx we have to identify. Now this can be compared to an equation, quadratic equation having ax square plus bx plus c equal to 0. So this is a quadratic equation. Now this equation is also a quadratic equation of this is quadratic equation of x. Similarly, this is quadratic equation of dy by dx. Okay. For any point in space xy, the solution of this equation will give the slope of the lines along which the derivatives of u and v are determinate. So by doing what we got this equation? By considering the determinant of the denominator of du by dx is equal to 0. So det a is equal to 0. That determinant is the slope of the derivative of u and v are indeterminate. We came from that situation. We considered that du by dx and du by dy or dv by dx or dv by dA are independent, and where in which condition that will be indeterminate? When the denominator delta a, the determinant of a is equal to 0, then only we will get these derivatives as indeterminate. Now from these conditions we got this equation. Now from this equation we can find out the slopes of the line, the slopes of the characteristic line. Now if I compare these two equations, what I am doing, I am comparing this a quadratic equation in terms of dy by dx with this quadratic equation. So if I compare that, what I can write? A is equal to a, this is a, and this is b, and this is c. So then what is dy by dx? Dy by dx is equal to minus b plus or minus root of b square minus 4ac by 2a. This is the solution for the quadratic equation, which is well known for everyone. Now in this equation, this determines the mathematical behavior of the equation. So we will take the determinant, okay, this root of b square minus 4ac, that we will take. Now this discriminant, the discriminant b square minus 4ac, okay, the discriminant b square minus 4ac will tell us what type of mathematical behavior the characteristic curve will be having. If the b square minus 4ac is greater than 0, then the behavior is like a hyperbolic system. Okay, so the equations are hyperbolic in nature. If this is equal to 0, then the equations are in parabolic nature. If this is less than 0, then the equations are elliptic in nature. Okay, so what we did till now, we have taken one quasi-linear system of equation, two equations we have taken, and we got two equations from the concept that the total derivative is continuous in terms of x and y, and then what we did, we made them in the form of a matrix form, and then using Cramer's rule we try to find the value of the derivatives of u and v in terms of x and y. Okay, now what we are doing is we are finding the behavior of the characteristic curve. And what is a characteristic curve? The curve on which the derivatives of u and v are indeterminate. That means the denominator, the determinant of the coefficient matrix is equal to 0. Using that, what we have seen is we found that this the slope of the equation is in the form of a quadratic equation. The quadratic equation, so this is what we have seen. This is the quadratic equation. The slope, we are getting the slope of the equation, the slope of the curve, the quadratic equation in terms of the slope of the curve. Now how to find the slope of the curve? We have this equation, the roots of the quadratic equation. This is the equation for finding the roots of the quadratic equation. Now if the discriminant is greater than 0, then we will have two real and distinct roots for this equation, and the system of equations that we have taken, the quasi-linear equations, they are hyperbolic equations. Now if b square minus 4ac is equal to 0, then the quasi-linear equations that we have taken, they are parabolic equations. If the b square minus 4ac is less than 0, then the characteristic lines are elliptic in nature. Now if det A is equal to 0, okay, if det A is equal to 0, I can have infinite number of things. Okay, I can have an infinite number of cases where the dou u by dou x can be indeterminate if det A is alone 0. Okay, if det A is alone 0, I can have an infinite number of curves, but the characteristic lines are only finite value. Okay, the characteristic lines are finite. We cannot have a infinite characteristic lines through a particular point. So what is the conclusion then? What should be the value of the numerator? The denominator is going to be 0. The denominator is going to be 0 means I can have an infinite number of values on the numerator, and for the infinite number of values I can get infinite characteristic curves, but that is not the case. The characteristic curve is finite, and so the numerator must also be equal to 0. Then only we will get one characteristic curve. Okay. Now, if I use this b, det b is equal to 0, I can find out what are the values of du, dx, dv. Okay, du, dv, dx, dy, which can give me the characteristic curve. What are the values of du, dv, dx, dy, for which the curve will be a characteristic curve. Okay. So if I use these two equations, then only I can restrict the curve to 1. Otherwise, it can have infinite number of equations. So this is about the characteristic curves. Okay. So what we have seen, the characteristic curves, if the coefficient matrix, the determinant of the coefficient of matrix is equal to 0, then the characteristic curves or the curves are called the characteristic curves. And if the b square minus ac, the in this equation, okay, the b square minus 4ac, the discriminant of this equation, based on this discriminant of this equation, we classify the characteristic curves as hyperbolic or parabolic or elliptic equation. Now the characteristic curves is defined by the partial differential equations that we have taken, the quasi-linear partial differential equations. So the quasi-linear partial differential equations are hyperbolic if this discriminant is greater than 0. The quasi-linear partial differential equations are parabolic in nature if this discriminant is equal to 0. If the discriminant is less than 0, then the quasi-linear partial differential equations that we have considered, they are elliptic in nature. So this is about the classification of partial differential equations. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.